Hi, this is Dave Pellerin of Amazon Web Services. Today I'd like to present to you how to accelerate product design with high-performance computing on AWS. We're going to focus on rapid innovation and how scale in high-performance computing on the cloud can result in faster product designs, higher quality, and reduced costs. We're first going to take a brief look at AWS infrastructure and how it relates to high-performance computing. We'll quickly move into talking about HPC solutions and some of the components that are available to you to create a complete HPC solution for design and engineering, for large-scale simulations, for example. We'll dig a little bit deeper into use cases for design and engineering specifically, and the landscape of HPC and how it relates to high-performance computing, instance types and storage and automation. We'll highlight a few customer success stories, and then we'll dive a bit deeper into best practices for performance, for getting extreme scalability and reducing costs, and some additional pointers at the end where you can go for additional resources and information. As an overview, AWS today is in 18 global regions and one local region with a total of 55 availability zones. This large amount of global infrastructure allows you to scale rapidly and scale large for your HPC simulation needs and for other needs, for example, big data that's used in the engineering domain. Each availability zone is segregated from others. We have separate floodplains, separate disaster zones. It really allows you to create highly available services within a region. And we have additional regions planned and availability zones in areas like Bahrain and Hong Kong, in Sweden, and a second GovCloud region for those ITAR-compliant workloads. Digging a little bit deeper, we have regional points of presence, over 100 of them around the world today. These points of presence allow you to accelerate delivery of data from S3, movement of data from S3 from region to region, CloudFront for content delivery, and this is all based on a private network, a 100 gig network globally, redundant private capacity that's available to you in your global expansion and in your global collaborations. Let's dive a little bit deeper into HPC and what HPC means for design and engineering and how high capacity and high performance can help you innovate faster. The most important thing about running HPC on the cloud and design and engineering workloads in particular is you're free from thinking about things like capacity challenges and technology roadmaps and technology refresh cycles, from large CapEx spending and difficulty in collaborating across organizations, into really focusing on innovation for your engineering and science applications. This is particularly true for globally distributed design teams that need to collaborate on large amounts of data and run large simulations in a secure manner. The components that make up an HPC solution for design and engineering on the cloud include orchestration and automation, for example, the use of methods for batch processing, for automating the clusters, and for managing jobs in, for example, a job queuing environment, as well as the raw compute that's necessary for high-performance computing. For example, next-generation instances, accelerated computing as well with GPUs and now FPGAs, the use of autoscaling to scale up and down, and other methods. On the visualization side, remote desktop as well as remote application and graphics streaming is very important for post-processing visualizations in the HPC area, as well as front-end design. On the storage side, you have many options, ranging from object storage in S3, which is highly scalable and highly cost-effective, to using elastic block storage and elastic file system to create file systems that are well-tuned for specific applications. And on the networking side, the ability to use enhanced networking, to use placement groups in support of tightly coupled workloads that we'll talk about in a few moments that require large amounts of traffic, large amounts of messages between different nodes in a simulation, for example. Underlying HPC for design and engineering is EC2, Elastic Compute Cloud. The important thing to understand about EC2 for these workloads is that you have many different choices. In a traditional HPC environment, you really have very few choices because you need to plan for the long term and deploy servers that may exist in a data center for many years. On EC2, on the other hand, you have a choice of instance types that that are constantly being updated and refreshed, newest generation processors, newest generation acceleration technologies, and the ability to optimize your choice of instance types for each application in your workflow. On the storage side as well, as I mentioned earlier, you have many options. On the right side, object storage. S3 is really where you should consider the vast majority of your data should be stored. It's highly durable, it's cost effective, you can lifecycle data from S3 into Glacier, and when needed, you can create high-performance shared file systems, either using a fully managed service, Elastic File System, EFS on the left, or by creating a file system using a combination of EC2 instances that act as filers and Elastic Block Store block devices that are used to create storage platforms, for example, a shared file system or distributed file system. And these file systems can be tuned for specific applications. On the data transfer side, you also have many options. How to get data into the cloud, ranging from physical means using AWS Snowball into synchronization types of use cases, for example, storage gateway or using third-party partner solutions for synchronization of data, and the ability to secure that data and have cost-effective data transfer, for example, using AWS Direct Connect and CloudFront for ingest and egress, respectively. Underlying many HPC applications is the need for high-performance networking. This is particularly true for tightly coupled workloads or workloads that rely on network-attached storage, for example, a shared file system. AWS has a proprietary network based on the Elastic Network Adapter. This is our latest generation of networking technology, delivering up to 25 gigabits per second in a cluster placement group. Highly consistent latencies, very high throughput, and the ability of this network to support HPC workloads, in particular those that are based on MPI, message passing interfaces, is excellent. And we've got benchmark numbers we can show for this. We've got examples of running tightly coupled workloads that I'll touch on in a moment. But it's important to know that you can run very high-performance, multi-node parallel types of workloads, for example, fluid dynamics, using AWS and using this high-speed network. To get the most benefit out of the high-speed network, you do want to use the latest generation operating systems, network drivers. You want to use placement groups. I'll touch on some of those aspects in a few moments. Another important component for HPC workloads, in particular for large-scale simulations, highly parallel simulations, is batch processing. And there's a number of options to consider in the area of batch processing. AWS Batch is a native service, a fully managed batch service that allows you to focus on applications, to scale out and manage a cluster of compute nodes on which you're running containerized applications at scale. Fully managed service, as I said, no single point of failure, highly scalable, and it includes a scheduler that can be specified with dependencies so that you can run complex workflows in a batch manner in a highly parallel way. And we don't charge anything for AWS Batch. You only pay for the resources that you consume. For more traditional scheduling environments in the HPC area, CfnCluster is an excellent option. And this allows you to really use existing schedulers, for example, SunGrid Engine, Torque, and Slurm, and others. And these schedulers can be automated and their use of the cloud be managed in a much easier way using CfnCluster. For example, CfnCluster can help you to automatically scale up and scale down a cluster in the cloud based on the number of jobs that's in a job queue. And it's open source, it's highly scalable, modifiable, and you can use it to deploy not only the cluster itself, but also perhaps the shared file system that is used with your cluster. And this is provided in a GitHub repository. You're welcome to download and modify this. It's an excellent solution for traditional HPC scheduling on the cloud. CfnCluster allows you to launch a cluster literally in minutes. It's based on CloudFormation, of course, and cluster creation, the full creation process will take up to 15 minutes, completely managed by CloudFormation. And again, it includes the ability to stand up not only the compute cluster and its scheduling head node, but also to create things like shared file systems and license managers and so forth, highly extensible based on CloudFormation. There are many options that you can choose in CfnCluster. For example, which operating system are you running? Which scheduler is going to be integrated with it? What's the type of storage, the IOPS required for that storage? Again, it's a highly configurable environment based on Amazon Linux, supports both CentOS and other distributions, and highly scalable and easy to use if you're familiar with traditional scheduling environments. On the graphics side, remote visualization is very important for many applications in the design and engineering space. And graphics can be used at the front end of the design, for example, in doing 3D modeling or doing 2D types of operations, for example, schematic capture in electronics, as well as on the back end. So the post-processing that's done, for example, after doing a series of parameter sweeps on a structural simulation model using 3D visualization to walk through those models, to turn them and explore them. So 3D graphics is very important for many design and engineering applications today, and it's used very well, tightly integrated with HPC workloads, right? So pre-processing to set up the model, processing the model using HPC, and then post-processing using 3D visualizations. And we have solutions for this on AWS, including remote desktop using our DCV product, and application streaming using AppStream that I'll talk about a little bit later. So to summarize these advantages for HPC, why you would consider HPC in the cloud. The primary reason to consider cloud for HPC, in particular for design and engineering, is scale. The ability to scale to vastly more compute cores in a simulation, for example, or to run many, many parallel simulations in the cloud is a very important benefit of cloud-based HPC for design and engineering. The choices that you have as well, and I'll touch on this again in a few moments, the idea that you can choose the right kind of IT infrastructure, the right kind of EC2 instances and storage architecture for each problem in your workflow, each application, is very important optimization that you can consider. And you can continue to re-optimize over time as new instance types come along. As your needs and your models change, you can quickly re-optimize and change your optimizations for those particular applications. And access to high performance. And high performance means high performance instance types that deliver high clock speeds and consistent performance, as well as the ability to scale up into potentially thousands of EC2 instances, thousands of cores. And HPC on the cloud can mean both tightly coupled, traditional legacy HPC workloads like fluid dynamics and structures, as well as more massively parallel, loosely coupled, or pleasingly parallel applications, typically using EC2 Spot, using large numbers of instance types to accelerate those highly parallel applications. Another important factor that I'll touch on in a few minutes is accelerated computing, using both GPUs and hardware acceleration using FPGAs. GPUs in particular have become very common in HPC applications, and they're available at scale in the cloud. We talked a moment ago about visualization. The ability to use 3D graphics and to do interactive design work in the cloud is very important. And I'll talk briefly about analytics. It's also important that you can begin to insert analytics and machine learning into your engineering process once you're in the cloud. Again, using data lake strategies, using machine learning. There's many sources of data in the design and engineering and the manufacturing world that can be effectively analyzed on the cloud at scale. So again, high-performance computing on the cloud, innovating faster, getting products to market quicker, whether you're doing semiconductor design or automotive design, general manufacturing. There's many, many use cases out there in which rapid innovation can result in higher quality products, faster time to market. And the ability to optimize costs. As I said, it's so important that you constantly optimize in your cloud deployments. Think about new instance types. Think about right-sizing your infrastructure for each application. There are many, many opportunities to optimize your costs. I'll talk briefly about collaboration. This is also important. I touched on this earlier. The idea that you have globally distributed teams, or perhaps just multiple teams in the same geography, that need to collaborate on data, either for doing analysis, big data analytics, or by actually doing collaborative design, running simulations, looking at results. And cloud can make this much easier and more secure. Focusing specifically on design and engineering, as I mentioned, The goal of migration to cloud, of using cloud and scalability, is to accelerate your time to results. And time to results really helps to reduce risk, right, in your engineering design. So scale higher, run more parallel simulations, run more simulations than you could have in the past. Don't spend lots of money to stand up a fixed amount of resources to do that. Scale up and scale down. So that scalability and that ability to dynamically change and optimize resources is very important. And this relates to automation. Use automation with some of the methods I described earlier, using AWS Batch and CfnCluster to automatically scale and resize and resource optimize your applications over time. And think about security. As I said before, this is very important. Using governance, using the capabilities of cloud to create secure, auditable, traceable environments, in particular when you're collaborating with third-party partners. And think about high availability. Think about using cloud to create a highly fault-tolerant infrastructure, disaster recovery, for example. Allow global stakeholders to have access to data in a controlled and secure way, including external stakeholders. Use our 55 availability zones in our 18 regions to get access to scale, but also to put the data locally for latency reasons or to provide a disaster recovery scenario. All right, let's talk specifically about use cases. I'm going to start by talking more generally about HPC and the landscape of use cases for high-performance computing, and then we'll dive in a little deeper into specific HPC applications. If we look at the full landscape of HPC, I've just illustrated a few sample applications across sectors that illustrate what HPC really means in terms of need for performance in certain types of infrastructure. And in this four-quadrant graph, the vertical axis really illustrates what is the network requirements of these applications. And this is important because you're thinking about what kind of infrastructure on which to run these applications. At the lower end of the vertical axes, you would see grid computing, distributed computing, loosely coupled, pleasingly parallel, right? Some call it embarrassingly parallel applications. And historically, these have scaled extremely well in the cloud, and some of the earliest high-scale workloads in the cloud have been things like genomics and proteomics and Monte Carlo simulations used in risk and financial services. These are applications in which a very large number of compute nodes are spun up. They're relatively independent. They're doing independent calculations, not a lot of communication between them. They scale extremely well. Using spot instances, using multiple availability zones, it's possible to scale to very, very large numbers of threads, of cores in these simulations on the cloud. If you move up to the clustered area, the tightly coupled area, these are applications that historically require a lot of network traffic. They require message passing. And these are applications such as fluid dynamics and seismic processing, structural simulations, where communication from node to node is very important. Many of these applications are based on meshes that are created. The meshes have to communicate from cell to cell to converge on a result, so they're very network intensive. Now, the great news in the cloud is that many of these tightly coupled workloads, in fact, all of the ones I show here, run quite well on the cloud today. They scale quite well, and we've got some numbers to back that up. So you should not be afraid to run clustered, tightly coupled, traditional HPC workloads on AWS today with enhanced networking, with placement groups, highly effective for tightly coupled, clustered workloads. The other axis, the horizontal axis, refers to really what's the data intensity of the problem. On the left side, these are applications that use relatively little data in terms of setting up and running a simulation. A perfect example of that would be a risk simulation. That's a Monte Carlo simulation. You're really only feeding a few numbers in. You're running random numbers against some computation kernel, and some numbers come out at the back end of that process. Other applications in this use a bit more data. Certainly fluid dynamics simulations and structures and so forth use more data, but they're not as data intensive as the applications on the right. The applications to the right either require very large amounts of data, for example, seismic processing or animation and visual effects, or they require extremely high IOPS. They require very fast read and write of things like shared file systems, such as you would find in semiconductor verification, for example, or deep learning. So the good news on both of these axes is the cloud can be extremely effective both for clustered, tightly coupled network-intensive workloads as well as data-intensive workloads. And this is driven by the applications that are scaling rapidly on the cloud today, including areas like deep learning. And the infrastructure, the services, the capabilities that are required for these cloud-native use cases like machine learning, deep learning, have benefits for all of these other applications. If we dive specifically into design and engineering and product engineering, we see a number of these use cases are found in product engineering. In fact, product engineering, design and engineering across sectors is really one of the largest areas of use of high-performance computing in the world. And again, these are areas like fluid dynamics used in automotive and aerospace and product design and medical devices, materials and structural simulations. On the high-tech manufacturing side, digital simulation, analog simulation, and verification of chips. These are applications that require increasing scale year over year as products become more complex. And in fact, even some of the other workloads that are not highlighted here, for example, animation and visual effects, are finding their way into the design and engineering area as we wish to do, for example, visualizations of products after doing some number of simulations. A great example of that in the graphics area would be in the energy sector, use of graphic visualization for seismic. In the automotive sector, doing things like car configurators, right, and 3D models that are developed after simulations. There are many, many examples like this that are used in design and engineering, and graphics is becoming more and more important for these applications. If we look at a traditional HPC stack that would be used in support of the applications that I just described, so not in cloud, but in a traditional on-premise or data center environment, you could simplify the typical stack to look something like this. And this is a very common pattern that's found across industries. It's certainly found in manufacturing and automotive and aerospace and semiconductor, in the energy sector. And these HPC stacks, they've evolved over literally decades to do what they do. Starting from the top, many of the HPC environments today do support remote desktop, so there's a wide variety of solutions in use today to allow remote graphics, either on a heavier weight graphics workstation or on a thin client device with browser-based solutions. The next box down, this is where your license managers live. For example, if you're using floating license managers that are used with ISV software that's provided by your CAE or EDA vendors, those license managers require typically multiple servers to have a highly available environment. In this box, you would also find your cluster head nodes. So, for example, your scheduler head node, your perhaps head node that's running file and data types of management solutions, right? Your configuration management systems might exist in there as well for check-in, check-out. So these head nodes are persistent. They have different requirements depending on the applications, but they need to be highly available. And then the next block down, your HPC clusters, right? So in a typical HPC environment today, you're going to have multiple generations of servers because they're being refreshed every year over time with a multi-year life cycle. You may have different clusters in there for different types of applications, but more typically, there is one sort of one-size-fits-all cluster that's built for the worst possible application in your workflow. Very high memory, high clock speeds, high network performance, and high-performance shared file systems. Again, this is a traditional stack. These stacks have existed for quite a long time, and they've grown, and as organizations grow and their needs grow, they've moved to multi-site operations, and really managing and maintaining these over years is very difficult, and it's difficult to maintain these at a high utilization, given the changing needs of design and engineering. When you migrate to the cloud, the first thing that you can think about is actually replicating that legacy environment in the cloud. And CfnCluster and other examples that we have in templates will help you to do this very easily. The first step, of course, is to create a virtual private cloud, a VPC, and then using automation, CloudFormation, within that VPC, you can easily create, literally within minutes, the same type of stack, the same type of infrastructure that you had in the on-premise HPC environment, including 3D graphics workstations that you can log into remotely, your license managers and cluster managers, your data management tools, and your repositories for check-in, check-out. All of that can exist in the cloud, really in the same kind of environment. And you can create those HPC clusters, of course. But the difference, the primary difference in this migration to cloud, this first migration to cloud of HPC, is the ability to automatically scale up and down, to scale up dramatically if necessary, and to create different types of clusters on demand using spot instances, using other methods, CloudFormation, to create clusters that are well optimized for each application in the workflow. And use CloudFormation templates, use Amazon machine images, use containers. There's many ways that you can make this a highly repeatable, highly templatized environment that you can easily stand up within minutes and create multiple of these clusters as needed for different users. You can also create shared file systems, and these shared file systems can be tuned for the unique application needs of every portion of your workflow. Some applications require extremely high IOPS, very high ratio, for example, of filers to storage devices. Others can take advantage of simpler management solutions or simpler data storage solutions like EFS or S3. And using capabilities of cloud and working also with our cloud partners, you can begin to operate in a hybrid environment using AWS Direct Connect, extending your network in a secure way, and beginning to use encryption, right, using your own keys to manage and maintain your data in a secure way, and the data from your third-party collaborators and IP providers, as the case may be. Let's highlight just a few customer successes that help to understand this need for scale that's growing across sectors, and also how AWS can help to access that scale and optimize applications for high throughput. I have a couple examples in aerospace I'd like to touch on. So the first example in aerospace is Boom Aerospace. And Boom is an organization that's building next generation supersonic transport types of devices, of aircraft, supersonic aircraft for the commercial sector. Obviously, doing this type of aerospace design, operating the supersonic realm, you need to do tremendous numbers of simulations, in particular fluid dynamics and structure simulations, to create a safe and performant, efficient aircraft. And so working with our partner Rescale, Boom Aerospace has been scaling their CFD models on the cloud. And they're typical models to do lift calculations, to do vortex calculations using fluid dynamics. Each of the simulations is 512 or more CPU cores, and some of them much larger. But the important thing to think about is that they can parallelize, right? So not only running a single job and then another single job and another job after that, but running all the jobs in parallel. I'll talk about this more in a moment, the idea that you can now parallelize, do parameter sweeps, right? And get the complete throughput of the application increased so that you get a much faster performance. And in their citing here, 600x speed up by parallelizing these jobs. Each job itself runs faster, but more importantly, we can run those jobs in parallel using the scale of cloud. Another example, this in the manufacturing sector, high-tech manufacturing, Western Digital, and specifically their HGST division, Hitachi Global Storage Technology, that was acquired by Western Digital. Western Digital has very complex design challenges. They design next-generation storage devices, including high-performance disk drives, SSD devices, and many services and devices related to large-scale storage management. There's two interesting areas to think about in the design and engineering realm at Western Digital. The first is actually around big data, the big data platform. To increase the yield and the efficiency of devices in the field and reduce failure rates, it's important for manufacturers to take advantage of data, field data, data from the manufacturing facilities, right? Bring that data into a single resource and do analytics on that data. And all manufacturers face this challenge of understanding data. Western Digital has been quite progressive in building on the cloud, using a data lake strategy, their big data platform. Now, this big data platform initially was using Hadoop, using such big data methods that were common let's say 2 to 3 years ago. More recently, Western Digital has been deploying machine learning against that data. And what's exciting about this is that once you've got a data lake in the cloud, you've got a big data platform such as Western Digital has built, you can continually re-optimize, rethink, and add completely different technologies. For example, deploying GPUs and TensorFlow to do machine learning against that data. Another area where Western Digital is working and getting great success and higher throughput is in the HPC area, in the simulation area. And they have many use cases that they've talked about publicly, including magnetics simulations using GPUs in the cloud, using very large numbers of CPUs to do drive head characterizations. There's many, many different types of simulations that Western Digital is able to scale in the cloud. And in some cases, the scale of these simulations has been very, very large. Single jobs for drive head characterization, for example, that are peaking out at 85,000 cores using spot instances for cost effectiveness. And this is a great example, there's many others like it, of using scalability in the cloud to accelerate innovation, bringing jobs that previously would have taken weeks in the on-premise infrastructure that was available down to hours in the cloud. Another example in aerospace, TLG Aerospace, are a consulting firm. They work with large aerospace companies to do design exploration and simulations. They bring in the requirements, the design configurations, and then they need to run many, many different scenarios. For example, fluid dynamic scenarios or structures against that model to determine which of the configurations are appropriate for actual manufacturing and flight testing. And obviously, the faster that they can deliver those results in those many, many different studies, the faster their customers can get to market with new structures, with new components, and new aircraft, right? And just like in the previous example, we've seen that TLG Aerospace has been able to scale dramatically. Each CFD study itself, using Star CCM from Siemens, can scale to 1,000 or more cores. But more importantly, they can run multiple of these studies in parallel for faster throughput. In the semiconductor sector, Cadence Design Systems has been helping customers in the verification area to more quickly deploy and get chips to market. And Cadence Design Systems has two strategies for this. One is their hosted design solution, shown on the right, HDS. This is a fully managed environment, Cadence managed, that helps customers do rapid simulations and verifications of chips. And they also help customers that are running in their own VPCs, in their own accounts in the cloud, to more rapidly deploy EDA solutions. Let's briefly touch on best practices for performance and scalability on the cloud. I've listed a few of the most important factors for performance, and these performance factors are true whether you're running in an on-premise traditional HPC environment or running in the cloud. You need to think about compute performance. You need to have high clock performance, in many cases GPU acceleration, or increasingly the use of alternative accelerators like FPGAs. Compute is really dominant. That's why it's called high-performance computing. But many of the applications today that we find in the engineering space also require very large amounts of memory. The memory needs, for example, in semiconductor verification or in structures, is just going up by the year. And so it's important that you have access to high RAM and high compute. You need high network performance, as I said before. You need the ability to have a variety of different storage systems for different applications. You've got to automate, right? And you need to have graphics for interactive applications. One of the more important factors, of course, is support from your ISV partners. And increasingly, the major ISVs supporting design and engineering have cloud-based solutions. They support deployment on cloud, including perhaps alternative license methods for cloud. So reach out to your ISVs, talk to your software partners, and talk about getting access to cloud and scalability of cloud, because scale is extremely important. When we think about scale, think about massive scale. Think about what you could do with 1 million cores, for example. And this is very practical today to launch tens of thousands, hundreds of thousands, even 1 million or more threads for a simulation, for example. Very practical in cloud, in particular using spot instances and using automation to move workloads rapidly to the cloud and scale them up. Another thing to think about, and I touched on this earlier, is the idea of grids of clusters, right? If you have tightly coupled workloads, CFD, for example, you should use placement groups. You should use enhanced networking. You should use traditional job schedulers to manage those. But when you want to scale out by having many, many parallel parameter sweeps, for example, use a grids of clusters strategy. Use multiple availability zones. Use things like auto-scaling. And really scale out, go wide. Don't put everything in one placement group, but scale it wide by creating multiple clusters, grids of clusters. And this allows you to expand the solution space. We saw that example with TLG Aerospace and others, the idea that you can now do many, many parallel studies, parallel parameter sweeps for increased performance and throughput. Also think about instance types. We are constantly developing and releasing new instance types, most recently the Z1D, which has up to 4 gigahertz sustained clock performance and a relatively high RAM. I've listed it here in both the computer optimized and the memory optimized because it really is both. And you have other instance types that are focused around storage performance, around graphics, around accelerated computing. So shape the compute to the work to be done. Don't shape the work to the available IT capacity. That's the important concept here. Z1D is an excellent example of a high-performance computing resource that you have available today. As I said, it's 4 gigahertz sustained performance, all turbo, high RAM relative to compute-oriented instance types, highly scalable, comes in multiple sizes. M5, also available now, and also M5D that has local NVMe storage. And we've shown for some specific applications, finite element analysis in particular, that the price performance of M5 relative to, let's say, M4 is dramatically improved. So generation after generation, we're getting higher performance and more cost-effective performance for HPC applications. Similarly with C5, also available with C5D with that local NVMe. Again, excellent performance improvement over C4 for fluid dynamics, finite element analysis, and other applications. On the computing side, the accelerated computing side, take advantage of, if you can, GPUs, in particular the P3s with the NVIDIA Tesla V100s. Talk to your ISVs about GPU support. These GPUs are available at scale on AWS today, and they're used across use cases for machine learning and AI, but also, as I said earlier, for accelerated engineering, for example, magnetic simulations and other types of simulations. FPGA instances, we don't have time to go into these in great detail today. There are other webinars and resources online about FPGAs, but they can be used for many applications in the high-performance computing space. It's early days for FPGAs in the cloud, but we're seeing use cases across sectors, engineering simulations, video processing, deep learning inference, for example. FPGAs are somewhat different than using traditional compute resources. You will use an Amazon machine image just as you do today, but you'll also use an Amazon FPGA image. And you'll typically work with a partner to develop or to deliver to you that Amazon FPGA image for use in a specific application. We have white papers and resources online going through some of these performance considerations, so I won't dwell on them too long here, but it's super important that you think about testing at scale. Don't start with simple, small benchmarks, micro benchmarks, but go for real large, chunky examples when you're testing HPC on the cloud, in particular for tightly coupled workloads like fluid dynamics and structures. Make sure you're using up-to-date libraries, MPI libraries, up-to-date drivers. Make sure that you're using placement groups if it's a tightly coupled workload. And if you're doing things like fluid dynamics, mesh-type problems, make sure that you've got a rational domain decomposition. The number of cells per core can be very important in getting high efficiency of these applications. For all HPC workloads, including scale out, think about OS versions. Amazon Linux, Linux 2, these will give you the highest performance on the cloud today. But the commercial releases like Red Hat will also give you extremely high performance because they do have the latest generation drivers for NVMe, for example, for networking built in. So make sure you're using an up-to-date modern operating system kernel, or that you've patched your older kernel with a newer version to get those high-performance drivers. And you have the ability to turn off hyperthreading, turn it on, to do things like use core affinity in pin cores and so forth. So we can provide additional details if you're interested in this, how to get the highest possible performance and tune your applications. Also think about using pricing models for tuning and optimizing your applications. A mix of on-demand, reserved, and spot instances can be highly effective in getting access not only to lower cost, but also higher scales. And our recommendation for HPC is that you use as much spot as possible. You'll save a dramatic amount of money, and you'll be able to scale higher and faster using spot instances. And we have partners. We have many partners, in fact, in the HPC space. This is just a few of them listed here. These partners can include managed service providers. They can include providers of technologies like NVIDIA and Intel. They include ISV partners like Ansys and Cadence and Siemens and others. Providers of HPC middleware solutions and automation solutions like Univa and Altair. So again, we have many partnerships. Please do visit the HPC landing page and learn more about these partners in the HPC sector. Lastly, I'd just like to point out a few additional resources that are available on aws.amazon.com. We've got white papers around HPC and how to tune HPC per performance. Specifically for electronic design automation in the semiconductor world, we have a white paper on how to deploy EDA in the cloud, a very important white paper for semiconductor customers. We have well-architected frameworks for HPC. We've got blog posts on AWS and at our partners that can help you understand how to operate at scale. And as I said earlier, we do have much more detailed information than I could possibly provide today on how to optimize performance of EC2 instances and storage, right, and use automation on AWS for HPC for design and engineering. So with that, I want to thank you and really enjoyed the session today. I'm here for a few more minutes for Q&A. If you have some, please let me know.